submanifolds. So let me first start with a construction of open books, of an open book. So that's a construction due to Giroux. And we start with, say, sigma d lambda, which we take to be a Stein or a compact Stein manifold. That's terminology of Giroux, so you can also say it's Stein domain. And well, it's also okay to actually take an exact symplectic manifold with convex boundary. And let's take a symplectomorphism of sigma. That is the identity near the boundary. So actually near neighborhood of the boundary, it should be the identity. And well, as mentioned, the idea that we have is of an open book is you have so the idea of an open book is that it's outside the codimension 2 submanifold. It is a fiber bundle over S1. So we start using these data. We start constructing the fiber bundle over S1, and then we just glue in the missing part, which is called the binding. So outside codimension 2 submanifold called binding, we have a fiber bundle over S1. So we start constructing that. And it's a bit an unusual construction because we want to have a nice contact form. So the construction goes as follows. So first of all, observe that the pullback of the symplectic form d lambda is d lambda. But of course, if we pull back the one form, then we might not get lambda, but in general we get lambda plus something that's closed. Now, you can actually assume that mu is actually exact by kind of Moser trick. And if you do that, then we can just consider sigma times r and mod out by the following equivalence relation. We take a point in, say, x phi in sigma times r, and we identify it with psi x, and then phi plus h. So here we have to use this function h, and we can assume that this function h is larger than 1 since we are in a compact manifold. So what we do is, as always for a mapping torus, you identify this piece with this piece, but it's kind of distorted if you want. And what's the good thing about this kind of twisted mapping torus is just, of course, diffeomorphic to the standard mapping torus. So the good thing is that we have a nice contact form, say alpha, which is just d phi plus lambda. So if you use this to pull back that form, you get the same form. So this has a nice contact form, and I claim now that this glues to, say, B, which is just d sigma times d2, and on d sigma times d2 we have the contact form beta, which is h1 times, okay, so you use polar coordinates on d2, and beta is h1 times lambda restricted to d sigma plus h2 r d phi. So this is inspired by kind of the contact form on a Lutz tube, but actually the functions h1 and h2 have the following form, so they're a bit different from a Lutz twist in dimension 3. So h1 should look like this, and h2 should look like this. So it grows quadratically here, and here it becomes constant. Okay, and well, since it here becomes constant here, you can actually see that it will have exactly the same form as that, because actually this form, if you go more to for say, if you go close near the boundary, it actually grows. Since we have assumed that we have a convex boundary here, you can you can take a Liouville vector field transverse to the boundary, and then you see that it's actually expanding there. So Okay, so A and B glue to a closed contact manifold. So I'll take now this one. So okay, I call this X. X is A along the boundary. Okay. So observe here that A and B have the same boundary. Since psi was assumed to be the identity near the boundary. Okay, and this is just my notation. I don't know whether this is good notation. I call this open of sigma psi. So an open book with page sigma and monogamy psi. Okay. So, okay, and the picture maybe that you should have in mind is, if this is sigma, then we construct a mapping torus. And we glue here with psi, or maybe with this strange gluing, and then we glue, afterward we glue in. So this is A, the whole thing, and this is then B, which is just d sigma times d2. So this is then the binding, if you want, and these are the pages. Okay, so that's the basic idea of an open book, and it carries a contact structure, right? I mean, we have a contact form on both pieces, and the claim now, this is the theorem of Giroux, is that every contact manifold, every co-orientable contact manifold admits such a description. So this is motivation, basically. So every co-orientable contact manifold admits such a description. Now,
what do you mean by that? So let's see.
Well, it admits
contact manifold is arbitrary.
So if M psi is always of the form open. So there are, for given M, okay, I'll say it like this. Given M psi, so maybe as the kernel of one form, then there is a sigma and psi such that M psi is, as a contact manifold, contactomorphic to open sigma psi. Okay, so as mentioned before already, this is not such a decomposition is not unique. But before I come to that, let me just say some words on symplectomorphisms, because I mentioned that we need the page and the we need the Stein page and the symplectomorphism, but symplectomorphisms that are interesting are kind of hard to get. So let me say something about that. So this is.
Can I ask you a question?
Yes.
Is it possible for small contact submanifold of coordinate 2?
What did he say? Could you say that again?
Is it?
What's small?
I mean, so this kind of theorem is if there exists small contact submanifold of coordinate 2, let's say in a double chart.
Yes. Okay, I see what you mean. No, well, I mean, if you just have a codimension 2 submanifold, then it doesn't mean that the complement fibers in a nice way. And so you need two things. The complement needs to fiber in a nice way. It needs to be a fiber bond over S1, and the pages need to be symplectic in a sense. So I mean, in a Darboux ball, I can always find the codimension 2 submanifold, but that doesn't mean that codimension 2 submanifold. And in this particular Darboux ball, certainly I can, if you want, I can find something that looks like an open book in this Darboux ball. But I mean, it doesn't extend nicely to the rest of the manifolds. So, yeah. Okay, so this is symplectomorphisms, and it's also well-known story. So suppose that we have a Lagrangian in a symplectic manifold, a Lagrangian sphere. Then, okay, by the Weinstein neighborhood theorem, a neighborhood of this Lagrangian sphere is symplectomorphic to T star Sn, if you want, with its canonical symplectic form. And then we can just look at the cotangent bundle of a sphere, and so there's a following claim. we have a symplectomorphism of this cotangent bundle, and it looks as follows. So it's called a right-handed or generalized Dane twist. It was also mentioned in a sense, but for surfaces, but the situation for higher dimensional manifolds is very similar. So, notation is a bit. So I hope for the people who know it doesn't matter, and for the people who don't know, well, it also doesn't matter. But so what you do is you take a point, and then if you take out the zero section, then what you could do, you could follow the geodesic flow, and that's what you basically do. You follow the geodesic flow with a speed that depends on the parameter, on the length of the vector p. So this is geodesic flow of pq with speed. Well, say g of p. I haven't defined g. So g is some function that looks like, at the zero section it's pi. So what I want to say is actually that such a map tau is actually minus the identity at the zero section, and then it drops off to 0. So this is p. So for large p it's the identity, and for small p it's minus the identity. So this is called the right, and tau is called a claim. There's no claim at the moment. This is a symplectomorphism. And it's actually called the right-handed Dane twist.
Can I ask one more question?
Sure.
So is there any kind of classification result of this such a pair, sigma psi?
Classification in what sense? The equivalence. So when are they equivalent? In dimension 3, yes. So let me first finish the definition. What do you mean by classification? Yes, I mean. Well, I'll give a claim, which is kind of the best thing that you can get, and then so called the right-handed Dane twist. So there's let's stop here for the story about symplectomorphisms. So there's much more to tell about symplectomorphisms, but maybe not in this talk. So now we define the notion of stabilization. So this is kind of the non-uniqueness in that part, and probably addresses your question. So definition of stabilization. So the idea is the following. So let's L now in sigma. So suppose that we have such an open book, and let L n in sigma and sigma 2n be a Lagrangian disk with Legendrian boundary in the boundary of say dl in d sigma. So the picture is like this. This is sigma, and then here we have a Lagrangian disk, and this should be a Legendrian. So if you have such a thing, then what you can do, you can attach an n handle. So what we do is we define sigma tilde, and that's sigma, and then glued along this Legendrian sphere. We glue an n handle. And the symplectic structure extends over that object. So this is also actually it's even Stein, although it's maybe safer to stay in the exact symplectic category. And sigma tilde contains a Lagrangian sphere. So it's say L tilde, and L tilde is has the form. Well, it has this. We have here this Lagrangian disk, and then on this Lagrangian disk we can just glue the core of the n handle. Core of n handle. So the picture you have seen now many times, so I think it's okay to like this. So here's my here's L tilde. Now, and it's still on the blackboard, neighborhood of L tilde looks like a cotangent bundle, so we can apply a Dane twist there. And that's what we're going to do now. So, okay, so now the definition. So the open book with page sigma tilde and monogamy, say psi tilde, so this is an extension of psi to sigma tilde, composed with TL, is this called stabilization. Of the open book sigma psi. So, okay, maybe some words of clarification here. So we have here L, so maybe, I don't know what this is. Okay, this is maybe, this is also sigma. So what we've done is we have attached an N handle, and then if you have Lagrange, so maybe you have here, okay, so psi is the identity near the boundary of sigma. So that means that we can extend psi to psi tilde by just putting it on the identity on the N handle. So psi tilde is the identity on N handle. Yes, so that's the extension. And then I think I've explained all pieces. Right? Okay, and then we have a proposition about this. Namely that the stabilization is actually contactomorphic to the original manifolds. So the stabilization say open sigma tilde psi tilde is, so this is contactomorphic, so they're not the same open books. To the contact manifold. And then we have, maybe in dimension 3 we have the following theorem. So M3 manifold, well, it should be closed and oriented. So then contact structures on say M3 up to isotopy are in one-to-one correspondence to, with open books of M up to stabilization. I hope this answers your question. So if it doesn't, then then you clarify your question, please. Is this your question, or does this answer your question? So what I'm saying is that we can't, so the open book is not unique. We can kind of attach handles if we want, and then we need to change the monogamy, and we keep the same contact structure, but that's the only way in dimension 3.
So there is no some similar statement in the higher dimension?
So I don't know such a statement. I'll give some examples later where it works. But so let me first point out some problems. So the symplectomorphism group in higher dimensions is not as well understood. So there are symplectomorphisms that are not Dane twists. So in dimension 2, of course, everything is a product of Dane twists anyway. So, but in higher dimensions that's not true. And so that could be a problem. Maybe you need other kind of stabilizations, but it's not really. Well, I mean, you can say a little bit more than this, but it's getting very technical, and so there's no complete statement like that in higher dimensions, or at least not that I know of. Okay, so whatever.
More basic question from a little while ago.
Yes.
You should probably know the answer to this, but so. You said that every contact manifold comes from an open book in this way. this is high dimension. So
Yes.
But if we just talk about smooth topology,
Yes.
not every manifold comes from is an open book, right?
No, but every odd-dimensional manifold is. Yes.
So this doesn't give an obstruction to existence.
No, not at all. So even-dimensional manifolds, there's some obstruction. Distinct to signature is some obstruction, but otherwise there's no obstruction. So that's unfortunate. You cannot do so much with that.
Okay, so this property, based on this proposition,
Yes.
so can you describe this procedure with a fixed ambient manifold?
A fixed ambient manifold. What do you mean? As a submanifold? You want the contact manifold as a submanifold of a symplectic manifold and then do this procedure, or what are you saying?
Yeah, something like that. I mean, here somehow a priori you change the ambient manifold, right? And
Yeah. So so you're saying if I have a symplectic manifold if I have a contact manifold with a filling, is that what you're saying? And then you want to ask how the filling changes? Is that what you're asking?
something like,
Then I can say the filling doesn't change actually, because you can.
Can you replace contactomorphic with isotope in some
Something
sense? But then to do that, you have to have know what your identification of the two manifolds is.
Yeah. So, well, okay. Let me. So there are different ways of seeing this. So I don't know whether it's a good idea.
here, in these terms, right?
Yes.
The left-hand side is purely...
Yes, but okay. So I formulate. Okay. So let me put it this way. This is a theorem of Giroux, and I know how to. So let me put it. If you ask me now, prove this, then probably I get in trouble. If you ask me, prove this, I can do it. No. So I mean here. Okay. So the way I prove this is I don't get really isotopy, because what I do is. Okay. So I see this operation as follows. So for stabilization, you need to do two things. I need to change the page. This can be seen as a contact surgery. For changing the page, and then you need to change the monogamy, which you can also see as a contact surgery. So if you look now at cobordism level, then this can be seen. These surgeries they have index difference 1s, and they actually correspond to handle cancellation, and that's the way I see it. But if you do it that way, then you don't only get contactomorphism. So.
Another way to do this is like you have a page, you sort of have a thickening of the page.
Yes.
And you have your Lagrangian.
Yes.
And you drill out a neighborhood of Lagrangian.
Yes.
If you sort of look a little bit carefully, you'll actually get exactly this. You'll have an open breaking.
Okay. So this is general for all dimensions?
If you drill out a neighborhood of Lagrangian/Lagrangian, I guess it depends on whatever it is.
Yes. So you can actually, but in this situation, you can usually assume that actually Lagrangian is Lagrangian in the page.
Yes.
So you first perturb, you first isotope your open book, such that
I'm not sure. Can you do this in higher dimensions?
No, you can actually do it actually with less problems in higher dimensions because.
No, you're assuming it's higher dimensions.
Yes. Okay. So, okay, not okay. Okay. So where was I? Maybe. I don't know. Okay, so open books are not unique. Maybe some remark, in case it wasn't obvious. It's not very important. I won't use it. But let me point out that if you have an open book with monogamy, let's say, is the product of two symplectomorphisms, then I can change. Then actually, I can cyclically permute the order. And yes, it's not very deep, but if you have never seen it before, then there's worth the effort of mentioning this. So if I look at the binding of the open book, then okay. So what's the monogamy? I take a vector field on S1, I lift it, and then okay. If I travel around, then I get the monogamy. But if this piece corresponds, gives me monogamy psi1, then this piece gives me monogamy psi2. And, well, it doesn't matter. I mean, it just start at a different point, and then I get the other one. But I only get cyclic permutation. So that's maybe worth to point out. I have some additional structure. So if I want, I can put the Dane twist here. But I don't care in this talk, actually. Okay. So now, the title of the talk was diagrams for contact 5 manifolds, so we're almost there. So let me point out why I said Stein, why I was so insisting on Stein. So for Stein surfaces, we have a description in terms of Kirby diagrams, and I would like to use that. So, okay, so what is it? The Thurston-Banach invariant was semi-defined now. So okay, let K in M3, okay, be a Legendrian knot. Yeah, okay, I just say what they are. Okay, so then the Thurston-Banach invariant of K is the linking number of K and K prime, where K prime is a transverse push-off of K. So what you can always do this, take the rape vector, so you start at the knot. Okay, so we have some knot. Okay, so Legendrian knots are always drawn like this. So we take the contact structure dz plus x dy, and then observe that, okay, so the x-coordinate is pointing inside the blackboard, is pointing, so this the x-coordinate is transverse to the blackboard, and then x is minus dz dy. So the slope of a curve, so this is Legendrian, means that the slope of the curve, Legendrian means that the knot lies in the contact structure, so it lies in the kernel of this form. This is now messy. Okay, let me write it. Legendrian knot. So the tangent. Okay, so the tangent bundle of K lies in the kernel of this form, and well, okay. So we see that the slope in a zy projection determines actually the x coordinate. Okay, so slope in zy projection or yz projection determines the x coordinates. So if I draw a Legendrian knot like this, then this is a complete description. I mean, usually in a knot projection you have no idea how deep it lies, but here you know exactly how deep it lies. Okay, and now the point is that what we can do is, so what is a Stein surface? It's a four-dimensional, real four-dimensional manifold with a Stein structure. So there are different ways of saying what the Stein structure is. So Stein means either, you can say it like it is a complex manifold that admits a proper holomorphic embedding into Cn, but then we take compact parts of it, so it's a bit messy. Or you can also say Stein manifolds are manifolds that admit a strictly pluri-subharmonic function. Complex of yes. Okay, so now this is a theorem of say Gompf. Yeah, you can also say Eliasberg. I don't know. So every Stein surface can be described as well by handle attachment, by say two handle attachment along a Legendrian link, say L, which consists of say knot components Ki, where the framing. I'm terrible. Okay, Legendrian link in S1, the boundary connected sum of S1 times D3, so number of copies. So this is actually, okay, let me explain later. So where the framing of each two-handle attachment is given by the Thurston-Banach invariant of ki minus 1. So there's no freedom in framing. So let me clarify this a little bit. So actually, D4 admits a clear Stein structure, just standard J if you want, and a spurious subharmonic function, a half x squared plus y squared. And then we can attach one handles. If you do that, then you get a boundary connected sum of S1 times D3. And then we can attach two handles, and two handles must be attached along Legendrian links and with a given framing. Okay. So maybe I should say that I think this is enough. Okay, so there are two remarks that I should make about this. Okay, so yeah, I say Stein surface all the time, and it's a habit of mine, but you should really think of it as, you can either say Weinstein or just exact symplectic, because I really don't care that much about the complex structure. So the remark is we consider sigma up to symplectomorphism. And the other remark is, so actually, from a diagram, you can get almost everything, well, not everything, but you can get a lot of information about the Stein, about invariance. So we can read of course, the homology, but we can also read of the characteristic classes. So maybe I should say this. So it's easiest to formulate if there are no one handles, so let's do that. So suppose sigma Stein surface is obtained as a Stein surface by two-handle attachment along a Legendrian link, just as in the theorem. Then the first Chern class of sigma, if we evaluate, okay, so each so each link component gives actually a generator of H2. So how should I say that? So we take a Seifert surface for a link component, you push it deeper in D4, and then you glue it to the core of the two handle. Then you get a homology class, and I'll write this homology class by. So the Legendrian link is maybe the union of Legendrian knots Ki, and then I write HKI. So this is the homology class belonging to that. And this is actually given by the rotation number of the Legendrian knot. So here I forgot to orient my... I always forget things. So, okay. So it needs to be actually an oriented Legendrian link, otherwise the statement doesn't make sense. But so for the rotation number. So what's the rotation number? So the rotation number can be defined by, so let epsilon be a trivialization of the contact structure. So say, well, I'm a bit lazy, so let's take a global trivialization. I mean, you should maybe care, but so then the rotation number of a knot Ki. So we can of course then look, and so the tangent vector of the Legendrian knot lies in the contact structure. So it has a winding number with respect to the trivialization, and that's what we do. So this is just the winding number of the tangent vector of. Sorry for the sloppy notation, but okay, I think I hope you know what I mean. Yes. So if we travel around the knot, the tangent vector represents some vector in this trivialization, and then we can look at the winding number. That's the rotation number. Okay, I think now I've defined everything. Okay, and then I can maybe I'll give an example because. It's stupid without examples. So, and how slow am I? How much time do I still have left? 25 minutes, okay, that's... Okay, so example. So this is, so you might know this, or at least I told some people last week what this is. So if we do here, if we, so the Thurston-Banneken invariant of this knot is -1, and so we have to do two handle attachment with framing -2, and then we get actually T star as 2. And maybe I should also say that this is other notation. This is just notation. So, okay, so if I draw a circle, then it means that we do two handle attachment along the circle. If I draw two balls, then it means that I do one handle attachment along these balls. So this is one handle attachment, and this is actually S1 times D3, so one handle attachment. Okay, so let's... Okay, now I can come to the diagram for 5 manifolds. Before I forget it, I should say that this is joint work with joint work in progress, unfortunately, with Van Ding and Hans-Jörg Geiges. Okay, I've given all ingredients, so you can almost guess what the title of the talk would now represent. What we just do is we can represent every contact 5 manifold by an open book with this page, a Stein surface, and we can represent every Stein surface by such a diagram. So that's what we do. So the idea is just combine these ideas. So. Write contact 5 manifolds as a diagram representing the page. So and well, okay, we need additional data for the monogamy. Okay, so what do we do there? So let me just give some motivation by a very simple example. And the simple example, well, okay, so first we start with a very general observation. So we start with an open book. Let sigma be any Stein manifold. So Stein manifold. And then we can look at the open book with page sigma and monogamy the identity. And let me point out that by definition, at least the definition I gave, this is sigma times S1 union d sigma times D2. This is of course the boundary of D2. So we can also write this as the boundary of sigma times D2. And now observe that if sigma Stein, then sigma times D2, well, if here some, say complex structure J, then here we have the complex structure J plus I. So this is Stein is actually subcritical Stein. So what we see is that open books with monogamy identity are subcritical Stein fillable, right? And so this is, and actually there's a stronger statement. So from due to Chidibak, I don't know. So he claims that every subcritical Stein manifold is actually split, meaning that's of this form sigma times D2, and so that means that M psi is subcritically fillable precisely when it admits an open book. With the monogamy, the identity. Now, so, okay, let's apply this observation to so maybe some examples. So we have here, we can look at this Stein's surface, and we can say this represents an open book. So this is the open book with page T star S2, monogamy the identity. And we could also look at something like this. So this is a different page, and actually, so pages are not even homeomorphic. And so we get some 5 manifolds. Okay, so this is 1, 2, 3, 4. So this is the D4 bundle. Sorry, this is the D2 bundle over S2 with order class 4. And well, that doesn't seem like looks very different, but actually they are. Well, they're not only diffeomorphic. You can check that rather easily. But they're actually also contextmorphic. So I'll come now to that, how to show that. So to see that they're diffeomorphic, just observe that, take that observation. So this is a D2 bundle over S2. So it can be seen as the boundary. Sorry, this is a contact manifold with page D2 bundle over S2, and it can be seen as a boundary of the Stein manifold. Well, T star S2 times D2. This is the D4 bundle over S2. So here you have the same story. And well, there are only 2 D4 bundles over S2. And they're distinguished by their second Stephen-Whitney class, and they're the same. So they must be diffeomorphic. Okay. But I'll come back to that later. So this is the notation that I will use. I'll draw a diagram, Kirby diagram. And then I write some words, or some, well, in this case, just the identity, and that indicates the monogamy. So maybe this is also an example, the empty diagram, which is just the open book with page D4 and monogamy the identity. So this is just S5 with its standard structure. But now, if you recall my story about stabilizations, then if we stabilize, what do we need for stabilization? We need a Lagrangian disk bounding a Legendrian sphere. Well, I know an example of that. So this is a Lagrangian sphere, and it bounds a Lagrangian disk. So if we do here, well, if we do the usual story, so if we apply, and we'll write it like this, TL. So this is the open book with page T star S2. And monogamy a right and a Dane twist. So this is a stabilization. So they're actually the same. Okay. So let me now apply these ideas and yes. The Lagrangian disk? I don't think there's any obstruction. No.
Lagrangian disk automatically.
Yes. You were talking about Lagrangian disk, huh?
Yeah. It's automatically.
Yeah, so the Lagrangian sphere. Okay, I don't know, but actually I don't care. For the stabilization?
So maybe a first question is, how do you draw the things you're sort of the things that you're Dane twisting along, or like the Lagrangian disk?
How do I draw them?
Yeah.
Yeah, so this is not so if there's only a single word, the Dane twist only consists of a single word, then there's no problem. So in general I would say there's no good method for this. So if you do something like this, is this maybe this is your question. So what's the order of the Dane twist, or how do I?
That's not what I'm asking. Are the only Lagrangian disks that you're doing this?
Oh no! I mean, in principle, I mean, so okay. So I don't know. I don't know the example. So I heard that there is an example. I don't know how to draw it. That there's actually a knot that bounds a Lagrangian disk, and I could also use that in principle. So the only thing is, I need the Lagrangian disk in the interior, and it needs to bound the Legendrian sphere outside. That's the only thing that I need. And so the only thing that I know by heart is this one. But actually, well, maybe later on you can actually see an example where you don't see the Lagrangian disk anymore, or it's difficult to see that it is the case. Okay. So is the story more or less clear? So I draw a diagram, and then I just give I don't know any other Dane. Okay, I do know other symplectomorphisms, but say the easiest symplectomorphism to understand are Dane twists. So what I do is I draw a diagram, and then I write down a word in Dane twists, and they will usually be very short words, just one letter words, but okay. Okay, so let me describe some moves for 5 manifolds. So the move is most easily described if the monogamy is the identity, and I'll assume that, and I'll point out where the problem is. So suppose that I have that a piece of my diagram looks like this, and the monogamy is the identity. Then I can stabilize So here's the identity, and here's a Dane twist. And then what I do is, near the boundary, the two-hand attachment, everything is the identity. So what I can do is I can perform a handle slide now. So this picture doesn't fit anymore, so I draw here. So what we're going to do is we're going to slide the left part over the right part. So perform handle slide. So let me draw one intermediate step. So here the identity, and here a Dane twist. So if you do a handle slide, it's useful to draw a parallel copy indicating framing, and it's a bit of a messy story if you want to do it compatible with the structure here. So you have to do something like this. So this is a parallel copy indicating framing. So now we slide, so I get a new picture. Okay, so then here's still the identity on this piece, and here we have still a right-handed Dane twist. And notice that we actually didn't do anything with this piece. So this okay. So since there on this piece there is a non-trivial monogamy, and this is a bit dangerous to move this around. Well, it's not dangerous, but it's hard to track to keep track of what happens. Okay, so on the other hand, I explained this once in a fair amount of detail, and then the next time I go more quickly over it. We could also consider this diagram, and then say stabilize here. So let me point out that that's maybe related to the question asked earlier. So we're going to stabilize. Well, okay, I need to draw it anyway. So this is. So here is the identity, and here we have the Dane twist. And note that this result is the same as that result. So, in other words, we have found a common stabilization, so they're contactomorphic. So the diagrams. So I draw it maybe very briefly. This diagram with the identity is contactomorphic to this diagram, also with the identity. So what have we changed? Well, we have added a zigzag. So, well, if you know how to compute these Thurston-Banneken invariants, actually what you see here is that we've changed this Thurston-Banneken invariant. So what we see is that the Thurston-Banneken invariant actually doesn't matter. So in the example that I gave earlier, you see actually that we have shown now that these are contactomorphic, right? So we can either take the cotangent bundle of a sphere or the D4 bundle over, say the D2 bundle over S2 with order class 4 in the form as in the diagram that I gave, and they will be contactomorphic if you take their open books with the monody and the identity. Okay, so maybe. Yes.
You explain the pictures one more time. So from second, what happens to the third and fourth?
This?
Yeah, from the second picture, what do you do?
In this picture, this is an independent picture. So this is independent. So this is a completely different picture, and I say, well, let's forget about this one, and then stabilize here, and then I get the same diagram. Yes. So I mean, in other words, so what I've done is I've performed here stabilization and then a handle slide, and I get this diagram. And here, what I've done, I've just performed the stabilization, and I get the same diagram. So in other words, they must be contactomorphic. Okay. Okay. So now for move 2. So move 2 will describe that actually. So the first move says that the Thurston-Banneken invariant doesn't matter, and the second move will say that the knot type doesn't matter. So let's start with a knot. So what we want to show is that we can change any overcrossing into another crossing, or the other way around. So suppose that you have a piece of the diagram looks like this, and now also with monogamy the identity, and now I want to show how to change the crossings. So okay, before that I should maybe say that. I call this operation, so from here we can maybe go there, and I call this destabilization. I'm not sure it's a very good word, so we take kind of this piece away. So you cannot always destabilize, it depends on the monogamy of the other one. And so there are a bunch of examples here, so but maybe you just forget about it. And so this is destabilize. It's just terminology. Okay, so what we can do is we do two things. We just perform a small isotopy, and we perform move 1. So isotopy plus move 1. So if we do move 1, then we can increase the number of cusps here. So we do it on some right piece, and then we slide it all the way back, and then we do something like this. Okay, and this is still the identity. Then I stabilize here. So stabilize. Near the red curve. And if we do that, then you get something maybe not so funny. Okay, so here it's still the identity, and here we have a Dane twist. And now we perform again a handle slide. And so perform a handle slide, and you see actually that we're almost done. So the handle slide will be okay, so this is a bit dangerous to draw this by heart. Okay, Okay, let me also draw the parallel copy for the handle slide. So the parallel copy looks like this. Okay, yeah, sorry, I'm getting lazy. So since they're Legendre knots, I don't need to indicate where overcrossings and undercrossings are, because it's already specified by the slope which one is deeper. But still, I want to draw it here because I want to show that it changes overcrossings into undercrossings. And boy, this one is this. This one is overcrossing. Sorry. Yes, so yes, okay. Okay, so this is the parallel copy, and then okay, I hope it's clear. So it's very easy to see, if you draw it on the blackboard, it's very easy to see that you now have performed what you did, because you can now just erase the stabilizing knot. So here is the identity, and here is the right hand Dane twist. So here, I call this destabilization as before. So you can just draw the same diagram without this knot and then stabilize there, and you see what happens. So what we get is, we get this diagram. Okay, and that's nothing. Boy. I hope I do it correctly, because otherwise it doesn't even... Okay, so wait, where am I? Wait, I lost track of... So this is correct, this is correct. So this is an undercross. Is it this? No, wait, help. Oh boy. Okay, second attempt. Okay, the second attempt just copies that knot and then I erase the part that I need. Or you can also say, if you just believe me, it's also okay, then I can continue. Yeah, so it's terrible. I never do this. So this one goes here. Yeah, so wait, this is correct, right? And then here, like this.
Yeah.
And now, okay, and now I just erase. What? That should be, wait, this one I should not erase. Wait, I'm confused. Wait. What? What do I do wrong? Did it change the crossing? I'm now confused. So wait, which is overcrossing? Oh yes, okay. Is it? Wait. So this one is that. No, I didn't do it right. Okay, then I. What? We believe you? Well, I can draw. I mean, I have it here, so then I am safe. But it's. So okay, what do you want? Do you want me to draw? What?
We can vote.
We can vote. So if you want me to draw this one, then it's so. Okay. Well. So people who are really interested should come in afterwards in front of the blackboard to check. Okay. So how much time is left? Nothing. Okay. Then a few more remarks about this.
Couple of minutes.
Okay. No, this took much longer. Okay. So what you see is if you do this, then actually if you do two handle attachment along any knot, then the rotation, the Topology doesn't matter, the knot type doesn't matter. I always get so maybe you get so two handle attachment. Along a Legendrian knot, and then monogamy identity. So you always get S2 times S3 if the rotation number is even, and you get the non-trivial bundle if the rotation number is odd. And actually, the Chern class is a full invariant. The rotation numbers are full invariant. So what you just do is, suppose that you have two knots with the same rotation number. Suppose that this story then shows this. So then, so maybe they're still different, but since they're knots, we can assume by this move that they're unknots, since we can change the knot type. Then the rotation numbers are equal. They don't change during these moves. And then we just decrease the Thurston-Banach invariant by the first move. At some point they're the same, and then by the Edelsberg-Fraser, the knots must be isotopic, so the result follows. Okay, that's one part of the story. Now you can do this story also in the presence of one-handles. That's a bit messier, especially in combination with the Chern class. What you can do is, so if you have a one-handles, then you also have a fundamental group. Now the fundamental group has some presentation, and what you can ask is, so suppose that I have two diagrams in it, which look completely different maybe, but suppose that they represent the same fundamental group. Then the diagrams, these one-handles and two-handles, they give a presentation for the group. Now if the groups are isomorphic, then by theorem of Tietze, there are moves that move these presentations to each other. Now you can also realize these Tietze moves on diagram level. But there's one, so that means that in a sense you get the result that the manifolds only depend on the fundamental group. But there's one thing that you need to keep in mind here, is that during these Tietze moves you sometimes add a relation. And adding a relation is adding a knot, which is very nice, but it amounts to taking connected sum with S2 times S3. So you don't really get that the manifold depends only on the subcritical fittable fittable contact manifolds only depend on their fundamental group, but they depend only on their fundamental group and Chern classes after taking connected sums with S2 times S3. And I don't know how many you need to take, so but since I already went over time, so let's keep it here. Okay, thank you for your attention.